Okay. Interesting stuff today we have. Oh, Abdul? Oh, that's Pedro. Nice for you to join us. 1, 2. Alrighty. Okay. Homeworks are going around. Today we do radiation exchange between real gray surfaces. Here's the timesheet. All right. So without further ado, let's go. Okay. Oh. You want that window open? Oh. Better. All right. Radiation exchange. Last time we did a radiation exchange between black bodies. This time we're doing a radiation exchange between opaque, transmissivity is equal to 0, isothermal, diffuse, gray surfaces. So these are real surfaces. Real surfaces. They're not black bodies. All right, so let's draw the drawing. Okay, here's one body. Here's the second body. All right, so this will be some area 1 and some temperature T. And this will be have some area 2 and some temperature T2. Now we need to find out what's going on here. Well, we're going to have some irradiation coming in and striking the surface. We'll call that G1. And because it's a real body, a portion of this is reflected away, and this will be rho 1 G1. Okay? So that's our reflected irradiation. And then because it's a body, it's got a certain temperature, it's going to emit, and that's going to emit at epsilon 1 EB1. Okay? And in order to maintain the temperature, it may be necessary to add or remove heat. So we're going to show this as the heat flux necessary to keep the body in thermal equilibrium. As you know in the homework problem that I just returned, there can be a difference between the amount of emittance coming off of a body and the amount of irradiation coming in. And so that will mean the body could either heat up or cool down. And so this heat will keep it at the isothermal state, T1. Similarly over here, we can have some irradiation G2. We can have some reflected irradiation, rho 2 G2. And we can have the emittance, epsilon 2 EB2. And similarly, we can have the heat flux, we'll show it in, to maintain the body at thermal equilibrium. All right, so what are we dealing with? Let's just list this again. First of all, the body is opaque. Meaning both bodies are opaque. That means tau is equal to 0. There's no transmissivity. They are diffuse. And alpha will be equal to epsilon, and in this case, alpha will be equal to epsilon, by the way, and rho plus alpha will be equal to 1. And Q prime is equal to the heat flux needed to maintain the constant temperature condition. All right, so now let's look at the radiation exchange between these two surfaces. All right. Recall radiosity. Radiosity is J. J1 was everything which was leaving the body. So that would be equal to rho 1 times G1 plus epsilon 1 E B 1. So that would be the radiosity of surface number 1. So the total energy leaving A1 that subsequently strikes A2 will be equal to this. Q1 to 2 will be equal to J1 A1 F1 to 2, where F1 to 2 is the view factor or shape factor of how shape 1 sees 2. And J is the total amount of energy leaving. Similarly, Q2 to 1 is equal to J2 A2 F2 to 1. If we apply reciprocity, we know that A2 F2 to 1 is equal to A1 F1 to 2. The net heat transfer Q12 is equal to the following. Q12 would be equal to Q1 to 2 minus Q2 to 1, which would be equal to A1 F1 to 2 times J1 minus J2. So now we have an expression for the amount of heat transfer that occurs between these two opaque isothermal diffuse spray surfaces, where epsilon is set equal to alpha and transmissivity is equal to 0. All right. There's only one problem with this perfect arrangement. What's that?
What are the view factors?
Well, that is a problem, but you'll solve the view factors. You had a whole homework that's due today on practicing view factors solving, right? Yes. You need to come up with an expression. All right, so let's do that. We're going to use an electrical analogy to do that. All right, I'm going to draw a circuit. All right, we know that Q1 to 2 is equal to J1 minus J2. over 1 over A1 F1 to 2. And this should look familiar to you, because this is what we have done in the past. So we're going to set up a circuit like so, and this circuit is going to have the current going across it, Q12. And the two nodes are going to be J1 and J2, and the resistance is going to be 1 over A1 F1 to 2. All right. And this is what we refer to as the space or geometric radiative resistance. What does this physically mean? It means that between the potentials of the two surfaces, this represents the resistance to the heat transfer from one surface to the other, which is based on how they see each other and their areas. Okay? That's what it means. Even though there's only A1 here, keep in mind that this could be replaced equally immediately with A2F21. Okay? So this is called the space of geometric radiative resistance. All right? So, that's one. But we're radiating from the surface itself. We have to take that into account. So let's do a first law on surface A1. All right, we know that energy in plus the energy generated must equal the energy out plus the energy stored. Okay? And what we're going to say is, look, there's no energy generation and there's no energy stored. So the energy which strikes the surface must be equal to the energy which leaves the surface if the isothermal condition is to be maintained. Right? That makes sense. Sure. So let's look at what comes in. Well, we have Q1 double prime plus G1 coming in. What leaves? Rho 1 G1 plus epsilon 1 EB1. Now you might say, okay, well, what is this exactly? Well, that represents the emissivity of a real surface. If it were a black body, its emissivity would simply be EB. But we can replace, in this case, its emissivity is E, capital E. But remember, capital E is equal to the emissivity. The capital E, the emissive power, is equal to the emissivity times the black body emissive power. In case you're wondering. Right? And we can go one step further too. And we will in a minute. Right? Okay? Alrighty. Okay. Now, okay, where am I? Okay, so Q, the heat flux, is equal to rho G1 minus G1 plus epsilon 1 EB1. And we're going to group these together. So this is G1 times, and I'm going to rewrite this. This is E1, epsilon 1, EB1 minus G1 times 1 minus rho 1. Simply adding an extra sign in there. But this is equal to alpha 1. And what we said is, in this case, alpha is equal to epsilon, so we're going to be able to replace this with epsilon 1.
Why in this case non?
Because we're not going to be dealing with spectral emissivity. All right, we're just saying it's one emissivity for the body. In which case, that's not an issue. Okay, just one, the total emissivity. What you all made this assumption on your homework, but that's not the case because there were multiple spectral emissivities for the body, right? In this case, it's just one emissivity for the body, so it works in that case, if you think about it. All right, so we're replacing this with the alpha, which is equal to epsilon 1, so or we can write Q1 flux is equal to epsilon 1 EB1 minus G1. Or we can write Q1 is equal to epsilon 1 A1, getting multiplying both sides by A, EB1 minus G1. All right, now we've got to express G in terms of J and E. We do that. So we're going to express G1 now in terms of EB1 and J1. So we know that G1, if we go back to our first law, or to the radiosity, we know that G1 is equal to J1 minus epsilon 1 EB1 over rho 1. All right, and that would be equal to J1 minus epsilon 1 EB1, doing the same thing. This then becomes 1 minus alpha 1, which would be equal to 1 minus epsilon 1. So we're going to divide this now by 1 minus epsilon 1. Then, Q1 is equal to epsilon 1 A1 times EB1 minus J1 minus epsilon 1 EB1 over 1 minus epsilon 1. And rearranging, we get the following result. We get the following value. Q1 is equal to EB1 minus J1 over 1 minus epsilon 1 divided by epsilon 1 A1. And we're now going to do the same thing. We're going to draw another circuit. And this circuit is going to look like this. And the nodes now, the heat transfer that occurs is Q1. This node is EB1. And this is J1. And this is 1 minus epsilon 1 over epsilon 1 A1. And this is known as the surface radiative resistance. What does that physically represent? Gio?
Not entirely sure.
Austin? Louis? Anyone?
Natural ability of the surface to resist heat.
Due to what?
Reflection,
Yeah.
radiation.
Yeah, due to the fact that it's a non-black body and it has real material properties. Its emissivity, its reflectivity, etc. Exactly right. So it is, this represents the imperfection of a real surface as compared to a black body. Now let's put them all together and this will become a little more apparent to you. Okay? This will become a little more apparent. We're going to do the combined electrical analysis. All right, we started off the class by saying, how does A1 see A2? And how much heat is exchanged between these two? Now, last time in class, if you'll recall, we said two black body surfaces seeing each other. The heat transfer is simply equal to A1 F1 to 2 times EB1 minus EB2, which is equal to sigma times A1 F1 to 2 times T1 to the fourth minus T2 to the fourth, right? That was for our black body. But now we have real bodies, and they're imperfect when compared to the black bodies. Well, we can draw all three of these circuits, and I'm going to do that now. All right? Over here is EB1. Over here is EB2. This is J2, and this is J1. Q1, Q1 to 2, Q2. Now these could be all reversed too. Okay? And the resistances are going to be 1 minus epsilon 1 over epsilon 1 A1, 1 over A1 F1 to 2, and 1 minus epsilon 2 over epsilon 2 A2. What we have here is how one surface sees the other. Now, what happens if it's a black body? This term goes away. There's no resistance here, nor is there resistance here. Okay, if they were both black bodies, there would be no resistance. And what would J be equal to? We'll go back to J. J is equal to what? Rho 1 G1 plus E1 epsilon 1 EB1. Well, what's rho 1 for a black body? 0. That term goes away. What's epsilon 1 for a black body? 1. So J1 becomes what?
1.
EB1. All right? So this surface radiative resistance goes away. And that's how it all fits together quite nicely. All right? So what does this mean? Well, it means that Q1 is going to be equal to Q1 to 2, which is going to be equal to Q2 if we have only two surfaces in play. And this will just be equal to some value Q. And Q, the heat transfer between the two surfaces, is going to be equal to EB1 minus EB2 over 1 minus epsilon 1 A1 plus 1 over A1 F1 to 2 plus 1 minus epsilon 2 over epsilon 2 A2, or three different resistances. And this then can be equal to sigma T1 to the fourth minus T2 to the fourth over 1 minus epsilon 1 over epsilon 1 A1 plus 1 over A1 F1 to 2 plus 1 minus epsilon 2 over epsilon 2 A2. And that is a relationship that you can use to evaluate the heat transfer that occurs, the radiative heat transfer that occurs between two surfaces that are opaque, isothermal, and diffuse. So, we can get the two temperatures easily enough. We can read the values of epsilon for the book, and we can get the areas if we know the surface geometries, and you can look up or solve for F1 to 2. Or conversely, it might be easier to solve A2, F2. So in other words, we now have the tool to be able to calculate the radiative heat transfer exchange, the net heat transfer exchange due to radiation between two real gray diffuse bodies. Okay? Questions? Okay. Yes?
In the book, it was talking about Kirchhoff's laws.
Pardon me?
In the book, it mentioned Kirchhoff's laws.
That's Kirchhoff laws for, well, go to Kirchhoff laws. In chapter 12, at the end of chapter 12, yeah, 776. What about it?
How does that apply to the electrical analog, or is it a completely different thing?
Well, what we did is we said that the radiation in this case is that for these particular surfaces, the emissivity is constant for the entire surface as the absorptivity is, okay? So we don't have any spectral variations. What happened in your homework problem where you have different values in that case. So that's the case, and we applied Kirchhoff's law here, where we said 1 minus rho 1 would be equal to alpha 1 because tau 1 is equal to 0. And then if that is applying Kirchhoff's law where the body is, there's no spectral variance in the absorptivity or the emissivity, then alpha 1 would be equal to epsilon 1. And we're able to go through this derivation to come up with this result right here. If you were working this with a body that had varied emissivity over a range, then you'd have a problem. Okay. So we're just assuming constant emissivity over the spectrum.
Cool.
Kind of done. I got one more thing. I have a lot of time too. One more quick topic that I want to cover. It's called the radiation shield. Radiation shields are kind of interesting things. We practice radiation shields on a lot of things. How many of you have ever had a thermos bottle and had it broken? Had a glass thermos bottle? Don't make those anymore? You know? I guess they don't. All right. Well, but thermos bottles, even if they're not glass, have the same basic property. We want to cut down on radiation exchange. Well, how do you do that?
Add more reflexes.
Yeah, you reflect the radiation back. You've been to, I'm sure some of you run road races where they passed out those little metallic type blankets at the end of the race to keep you warm. What side do you put next to you?
Shine stuff.
Why?
Reflects better.
It reflects the body heat from your skin, which is radiating back. Okay? That's what radiation shields do. In thermos containers, there is a reflective, they're usually evacuated to avoid convection. The surfaces where they come in contact are well insulated, typically with some sort of rubber surface to minimize conduction. And then there is a shiny surface in there, a radiation shield, to minimize radiation. So all three, the typical thermos bottle takes into account all three modes of heat transfer and knowledge of those three modes of heat transfer to reduce the amount of heat exchange between whatever's kept warm or cold in the bottle and the surrounding area. So how does this radiation shield work? Surface 1, surface 2. And in between, we'll have some shield. So let's label these. This will be A1, surface A1 at some temperature T1, some emissivity E1, epsilon 1. A2, T2, and emissivity epsilon 2. And then here, this will be our radiation shield. And this will have some emissivity 3, and we'll comma 1 facing side 1, and emissivity 3, comma 2 facing side 2. So radiation is blocked or cut down as it tries to go from field 1. So the purpose is simply to reduce the net radiation exchange rate between surface A1 and A2, and we're going to try to do that by having a low E and a high reflectivity. You've heard about low E before, or it should be pronounced low epsilon, but people call it low E. All right, so now we're going to draw the network for this, and it'll look like this. right, and we'll start over here and we'll label things. So we'll have EB1, and we'll have J1. And then we'll have J3, 1, comma 1. And we'll have EB3, which is the body itself. Over here we'll have J3, 2. Then we'll have J2 and EB2. And we'll have 1 minus epsilon 1 over epsilon 1 A1, 1 over A1 F1 to 3. We'll assume the sign is the same sign on both sides. Then we'll have 1 minus epsilon 3, comma 1 over epsilon 3, comma 1 A3. We'll have 1 minus epsilon 3, comma 2 over epsilon 3, comma 2 A3 on this side. Then we'll have 1 over A2 F2 to 3, and then 1 minus epsilon 2 over epsilon 2 A2. And depending on the low E, if has a low emissivity of this surface, then the numerator is larger and the denominator is smaller, making the resistance greater, the lower the E. And what you end up with is the net heat exchange between surface 1 and surface 2 now has 1, 2, 3 more resistive terms, and these resistive terms can be very considerable, and they will greatly reduce the amount of heat transfer that goes between the three. And this is the whole idea of radiation shields. Okay? All right. Let's take a moment to reflect on the homework. Does anybody, first of all, let's spend 5 minutes. The homework problem that I gave you, there's no way to do these, there's no way to do this stuff other than just to do it. So any questions real quickly on 37? I had a moment the other day with, does everyone know how to do problem 1? Have you done problem 1? Let's take a quick look at it, shall we? Let's take a real quick look at problem 1. I'm going to, I'll just write underneath this in case you haven't got it. All right, so problem number 1. This is kind of an interesting problem. This was a test problem, by the way. Although I will tell you that the test problem actually did have you find only the first part of the problem was to find the areas, the shape factors. Then you had to solve for the radiation exchange. All right, so this is surface 2. This is surface 1. No, excuse me. This is surface 3, surface 1, and these two were surface 3. And you were asked to find a bunch of shape factors.
You've got 2 surface 3s.
Thank you. These two make up surface 2, correct? Mm-hmm. All right. And you're asked to solve for F1 to 2, F1 to 3, F2 to 1, F2 to 2, F2 to 3, F3 to 1, and F3 to 2. Okay. So let's do an easy one first. What's F1 to 3? And what's F1 to 2? Just by inspection. Well, let me ask you a question. Let's go back a second. F1 to 1 plus F1 to 2 plus F1 to 3 must be equal to 1. Can surface 1 see itself?
No.
How does that pipe see the surfaces?
Equally.
Equally. It sees each one of the 3 surfaces equally. So that means that F1 to 2 is equal to 0.6667, and F1 to 3 is equal to 0.3333. Agreed?
No.
No?
Isn't the heat transfer to each surface is equal, so wouldn't it be like?
I didn't say that because each surface,
Times the
each-
factor?
that would depend on the emissivity and other factors. I'm saying, what I'm asking you in this problem is to solve for the view factor, okay? The view factor is only one component in the amount of heat transfer that occurs. Other things include the emissivity, the surface material conditions, and includes the temperatures, okay? We're not there. All we're doing right now is figuring out F's. The problem that the test problem which this came from actually had 3 different emissivities. The cover had one emissivity, the sides had another emissivity, and the pipe had a different emissivity, okay? And there were different temperatures.
How do you know it's the view factor that, like, how do you know each has, isn't it the view factor times the area that's equal?
Reciprocity says that the area of one times the view factor of one to another equals to the area of the other times the view factor in reverse. Okay, that's what reciprocity says. Okay? We're not using reciprocity in this case. What are we simply doing? We're doing simply an analysis. This is the puzzle type of aspect of this. You've got one, this surface sees these 3 surfaces equally. It's an isosceles triangle, and it says an isosceles triangle. Measures 45 centimeters on each side. Okay? And it's centered in the center. Pardon me? Equilateral. Yeah. Thank you. Equilateral triangle. Equal sides. Each side's the same. And what did I say?
I think it's 2 sides.
Yeah, that's right. You're right.
It's a
Equilateral
specialized
triangle. So each one of these are the same. So 1 can't see itself. So 1 sees twice as much of 2 as it sees of 3. And therefore, that's why the view factor is 0.667. The other is 0.2333. Scott, I don't think I've convinced you on
It
this.
doesn't seem inherently obvious.
I see it inherently obvious. It should be obvious.
Well, let's you and I talk
It
after.
also sees twice as much area, so
It is twice as much area.
you need double the view factor then for it to see twice
It
as much.
is twice as much area, that's why the view factor would be twice as much, okay? Remember, what is
You're
F?
gonna multiply by the area, don't you?
Yeah, but not right away, all right, not right away. All right, well, okay,
Let's keep checking.
so we have F1 and we have F1 to 3. We can also, now we're going to multiply by the area, and we know that A1, F1 to 2, would be equal to A2, F2 to 1. So we can solve for this. We also know that A1, F1 to 3 would be equal to A1, 3, F3 to 1. So we have that one. Okay?
So then you get F21 equals F31?
F21, 2,1 equals F31?
Yeah.
No. No. 2,1 does not equal 3,1. 2 does not see 1 like 3 sees 1.
Doesn't it though? Because
No, because 2 is both sides. 2 is both sides.
but if you just divide by those areas, if you get F21 and F31 alone there,
Yes,
And then you plug in-
F31, you'd solve for F31 would be equal to A1 over A3 times F1 to 3.
yep, and then F21 is A1 over A2, F1 to 2.
F21
A2 is twice A3.
is equal to A1 over A2 times F1 to 2.
All right, now plug in F12 and F13.
Yeah, no, you're right, because numerically they come out to be the same. Yeah, numerically they come out to be the
So
same.
that's what I was just saying, it's not inherently obvious to me, because those two are the same, that F13 and F12 would be double each other. Like, that doesn't seem like something that I could just make a jump and be confident in.
Well, then do out the math.
All right, well, we got started. We got started here. Are you leaving already? Oh, you just, I tell you what. All right. Have a good day.